Okay, so let's have this example right here. So in this example, we would be selecting the lightest W10 section that will resist the given load. So of course, we have loads here. So the member is 7.5 meters long and is assumed to have one line of holes. So I'm sorry for the typographical error here. So holes in each flange and two lines of holes in the web. So as you can see, this is one flange, one flange, one flange, and one flange. So it has one line of holes each and two lines of holes in the web. So as you can see, this one right here is the web and we have two holes in here. Okay, and assume that there are four bolts in each line. So this is to be its front view and this is to be its side view. So per line, it would be having four bolts each line. Okay, so there, and it is also said here that we would be using A992 grade 50 steel, and by that itself, we already have our material strength parameters here. And of course, we must have diameter bolts. So in here, guys, we will be using 22 diameter bolts. So this should be in millimeters and not in meters. Okay, so for our point dead load, so our point dead load is to be 780 kilonewtons and our point live load is to be 1200 kilonewtons. And we would be using both ASD and LRFD method. And in this example right here, we would be neglecting block shear since the edge distances here are not given. So there. And once again, guys, the first thing that we would be doing right here from this slide right here is for us to list the parameters involved. So there, and from that our Fy, so writing them at the upper right corner of our screen, our Fy is to be equal to, so once again, we are to use A992 grade 50 steel. So going back to this slide right here, this one right here is to be for A992. So A992 grade 50 steel. So meaning that our Fy is to be equal to 50 KSI and our Fu is to be 65 KSI. So I would just be writing them here. So 50 and our Fu is to be 65 kips per square inch. So KSI and KSI. And since we are in the Philippines, guys, that follows metric units, we must convert this first into metric, which is in terms of megapascal. And for us to convert them, we must just multiply it by our conversion factor of 6.895. So times 6.895 megapascals per KSI. So KSI would just simply cancel out. And with those, guys, I would just be erasing this one right here. And with those, this is now to be equal to, so looking at the calculator to your left, guys, so 50 times the conversion factor of 6.895, that is to be equal to 344.75. And for our lessons and in our quizzes, I would be rounding them to the nearest whole number. So this is now to be equal to 345 megapascal. And as for our Fu, I'm sorry, this should be Fu by the way. So this is to be our ultimate stress, and that is now to be equal to, so once again, looking at the calculator to your left, that is to be 65 times 6.895, and that is approximately equal to 448.175. And rounding them to the nearest whole number, that is to be 448 megapascal. So these are to be the parameters here. So what parameter do we need here? So we also have your 22 diameter bolt. So I will just be writing it here. So 22 diameter bolt. So take note, guys, that this dimension right here is to be the diameter of the bolt and not the hole. And from this slide right here, if we are to use 22 diameter bolt, so I would just be changing the color. So if we are to use 22 diameter bolt, the standard diameter of the hole should be 24 So from that, guys, the nominal diameter of the hole from this one right here is to be 24 millimeters. But take note guys that according to the National Structural Code of the Philippines, the diameter of the hole that you would be making use is that of the nominal diameter plus another 2 mm. So once again, this is from AISC and this one right here is from NSCP. So from that, the diameter of our hole, so let's say our each diameter or the hole diameter is to be equal to 24 plus 2 mm, and that is to be equal to 26 millimeters. So this is to be the hole diameter that we will be making use. So hole diameter. So that is to be 26 mm. Okay, so what else? So I think we are already done with our part 1. So this is to be our part 1, which is list parameters. Okay, so for our second step, guys, what we would be doing here is that we would be getting the load combinations. So load. And from that, guys, our dead load that is listed here. So RP, DL is to be equal to 780 kilonewtons. And for our point live load, that is to be 1,200 kilonewtons. So the load combination for LRFD, so in LRFD, your PU is to be equal to, so it is either 1.2 dead load plus 1.6 live load or 1.4 dead load. So whichever would give you the higher value. So I wouldn't be substituting them in our solutions anymore, but I would be typing them in our calculator. So looking once again at the calculator to your left, 1.2 times dead load, and our dead load is equal to 780, plus 1.6 times live load, and our live load is 1,200. And from that, guys, our answer here is to be equal to 2856 kilonewtons. So that is for this first combination right here. And as for the second one, so this is to be equal to, so 1.4 times our dead load, and our dead load is to be equal to 780. So with that, our answer here is to be equal to 1,082 kilonewtons. By inspection, guys, we can see that this one right here would give you the higher value. So meaning this one right here governs. Okay, so that is for LRFD. And as for your ASD, so wait, I will just be moving it here. So for our ASD, the value for our PA is to be equal to, so it is simply the service load or the unfactored load. So that is basically dead load plus live load. So there, and looking once again to the calculator to your left, that is basically equal to 780 plus 1,200, and that would give us an answer of 1,980 kilonewtons. So this is to be the values that we would be making use right now. So 1,980 and 2,856. Okay, so moving forward, guys, so we are now on step 3. Step 3. And according to this slide right here, our step 3 is for us to solve for AG using these formulas right here, which we have derived a while ago. But let's just derive them again. So once again, in LRFD, so in LRFD, so let's determine the gross sectional area in terms of GSY. So GSY, this is for gross sectional yielding. So for LRFD, that is to be equal to PU is equal to phi PN, and our PN is equal to FY times AG. And since we are solving for gross sectional area, so I would just be rewriting it here for us to have a better solution. So by the way, number 3, determine AG. Okay, so there. And once again, we are solving for AG right here. So for our AG, this is to be equal to PU divided by phi times Fy. And substituting known values, guys, our AG right now is to be equal to, so PU is to be, once again, 2856 So from that, this is to be 2856 kilonewtons. And for phi, our phi is to be equal to 0.9. And our Fy is to be equal to, what is Fy once again? That is to be 345 megapascals. So 345 megapascals. But if you can remember guys, megapascals is equal to newtons per millimeter squared. So for us to arrive at an answer of millimeter squared, newtons must cancel out. So with that guys, we must convert this load right here to newtons first. And to convert it to newtons, just multiply it by 1000. So there, and solving for our AG in cross-sectional yielding in LRFD, that is now to be equal to, so 2856 times 1000 divided by 0.9 divided by 345, that is to be equal to 9198.07. 9198.07 millimeters squared. So this is to be the minimum area that we would be needing for our member to resist cross-sectional yielding in LRFD. Okay, so let's solve for ASD. So for ASD, once again, our PA is to be equal to Fy times AG. So this is to be your PN. And we would be dividing it by our factor of safety omega. And once again, in GSY, our omega is to be equal to 1.67. So I would just be writing the phi here. So phi in cross-sectional yielding, that is to be equal to 0.9. Okay, once again, solving for this one right here. So for your PA, guys, for your value for your AG, cross-multiplying. So AG is now to be equal to PA times omega divided by Fy, and substituting known values once again. So AG, this is to be equal to, so what is PA? So we have determined that already. Our PA is to be equal to 1980. So 1980 kilonewtons. But once again, let's convert this to newtons. So times 1000 for it to be converted to newtons. And times omega, and once again, our omega is to be 1.67. So 1.67. And we would be dividing this one right here by our Fy, and our Fy once again is to be equal to 345 megapascals. So solving for this equation right here, our value for our AG is to be equal to, so looking once again to the calculator to your left, so 1980 times 1000 times 1.67 divided by 345, that is now to be equal to 9584.35. So 9584.35 millimeter squared. So there. So if these two are only to be your basis, so meaning that your ASD would convert. But take note guys that we are still on the cross-sectional yielding part. So we have not yet solved for the tensile rupture strength or our tensile rupture parameter. Okay, so for our tensile rupture, so TRS. So going back to this one right here, this is to be our working equation. So for me to save some time, I would just be copying this one right here, and I will just be pasting them in our slides. So once again, this is to be for LRFD. So I would just be typing it here first. So LRFD. By that guys, our AG or our gross sectional area is to be equal to our PU, and our PU once again is to be equal to 2856. So 2856 kilonewtons, and convert this once again to newtons by multiplying 1000, then divide this one by, so what is the value for phi? So take note guys that your phi in tensile rupture stress is to be equal to 0.75. So from that guys, this is to be 0.75 times FU, and our FU is to be equal to 448 megapascals. So substituting it here, 0.0448 times the shear lag factor U. So what is to be the shear lag factor U of our problem? So going to this table right here, we would be searching for the shear lag factor U. But if you can read here, guys, number 1 states that all tension members where the tension load is transmitted directly to each cross-section elements by fasteners or welds. So in Tagalog, kapag lahat daw ng connection nakadistribute sa lahat ng members, you would be using this one right here. And as you can see, guys, in this part right here, all of the bolts are fastened about every member of your section. So it may be this flange right here, this flange, this webs, this flange, this flange. So they are distributed. So with that, guys, we would be making use of this shear lag factor right here, which is 1.0. So from that, this is to be 1.0. Okay, and as for the areas of the holes, guys, so these ones right here are the areas of the holes. So this one right here, this one, this one, this one, and this one. And for the area of the holes, guys, that is basically equal to, so the number of bolts, I mean, let's say that this one right here, so this area right here is to be equal to the diameter of the hole times this particular thickness right here. So let's say that that is to be thickness of the flange. That is for this one right here. And as for this area right here, that is to be the diameter of the hole times the thickness of the web. So there. But take note, guys, that since we are designing, we still don't know these values right here. So we still don't know the thickness of the flange and thickness of the web. So what we are to do here is that we would be getting a trial section from our GSY that we can use for us to check if that section is adequate here. Okay, so with that, guys, we would be making use of this particular table right here, which is the AISC shapes database. So that is to be this particular table right here. So wait, so it would be this one. So you can download this in the description below, or you can just message me. Okay, so in this AISC shapes database, this would give you the sections that you need and, of course, the parameters that you need concerning that particular section. Okay, so once again, by the problem, guys, so going back once again to our problem, we are to select the lightest W10 section. So meaning, of course, we would be searching for W10s in the AISC shapes database. Then another parameter here that we would be needing is that this cross-sectional area. So we would be searching for W10 sections that has this cross-sectional areas right here. So let's say we would be searching for 9584, guys. So going to this Excel file right here once again. So I would be pressing Control F and I would be typing W10X. So from that, guys, I can now see all of the W10s in here. So it would be this ones right here. So I would just be highlighting them. So these are to be the sections that we can choose. So there in this table right here, these are to be its weight. This is to be its area, its depth, its base of the flange, thickness of the web, its and thickness of the flange and whatsoever. But take note, guys, that these parameters right here are in terms of inches, since this is to be in English unit. So it is either that you would be converting these ones right here in terms of millimeters squared or millimeters, or better yet, just scroll to the right. So scrolling to the right, so I would be scrolling up to the right up until I reach this point right here. So from column CG onwards, all of these are in terms of metric already. So these ones right here are already converted into millimeters. So we have here our weight, area, I should say. So meaning that these areas right here are in terms of millimeters squared. So from that, guys, for you to remember, so as you can see, the area that we would be taking into consideration are that of 9198 and 9584. So since 9584 is to be the one that has a higher value, let's use that. Okay, so let's search for the value here nearest to 9584. So as you can see, we have here our section W10 by 49, which is 9290. And we have this W10 by 54, which is 10,200. So as you can see, 10,200 is greater than 9584, I think. So there. Okay, so let's use this one right here. So what we need in this part right here for W10 by 54, so I would just be highlighting it with another color. So let's say green. So we need the area here. So I would be highlighting it once again with another color. Let's say blue. So this is to be, I think orange. So we need the area. We need the base of the flange, I think. We need the thickness of the web. And we need the thickness of the flange. So this one right here. Taking those into consideration, guys, I would just be writing them in our blackboard. Okay, so from that, guys, for our area of the hole, so in this one right here, considering this setup right here, so I would just be copying this to the next slide for us to better visualize it. So I would just be putting them here. So for the area of the holes, guys, for this one right here, area of the holes is to be equal to, so we have 4 holes right here that is located at the flanges. So from that is to be equal to, so once again, the diameter of our holes is to be 26 mm. So 26 mm times, so what is to be the thickness of the flanges, so that is to be 15.6, which is this one right here. Then we would once again be multiplying them to the number of holes. So this one right here is just to be the area of one hole right here. But since we have 4, we would be multiplying this by 4. Okay, and as for the web, so we would be adding here, so plus 26 once again. So since that is to be the dimension of this one right here, so 26 times the thickness of the web, and the thickness of the web as per indicated here is to be equal to 9.4 mm. So times 9.4. Okay, and what else? So we have 2 holes right here, so we would be multiplying this once again by 2. Getting rid of this so that we can substitute this one right here. So this is to be our equation already. So what I am going to do here, guys, is that I would be designing it in LRFD, and I would be checking its adequacy in ASD if it is already adequate. Okay, and from that, guys, our answer here is now to be equal to, so for your AG, and looking at the calculator to your left once again, so that is now to be equal to 2856 times 1000 divided by 0.75 times 448 times 1 plus 26 times 15.6 times 4 plus 26 times 9.4 times 2. So with that, guys, our answer here is 10,611.2 millimeter squared. So this is to be the required area in LRFD. So for your ASD counterpart, just do this again, but in terms of PA and omega, and you would be arriving at a certain answer. But once again, what I would be doing here is that I would be designing it in LRFD, and I would be checking its adequacy in ASD later. Okay, and as you can see here, guys, that this area right here is greater than this area right here. So meaning that in terms of tensile rupture, this section right here is inadequate, since once again, its area is to be less than the required area for tensile rupture stress. So what we will be doing here is that we would be choosing another section. So for us to choose another section, let's bring this out once again. So take note, guys, that the required area is to be 10,611.2. So we would be going back here. So from that, we would be choosing the next section. So for the next section, guys, what is to be the nearest value that is higher than 10,600? That is to be 11,400, which is this one right here. So meaning we would be making use, we would be trying this particular section right here, which is W10 by 60. Okay, so with that, guys, we would be needing this value right here. So let's say that this value right here, which is the AG, the BF or the base of the flange, the thickness of the web, and the thickness of the flange. And I think it is better for us to check, to get the value of the radius of gyration already. So our radius of gyration here is to be equal to 112. That is for the radius of gyration for Rx, and for the radius of gyration for Ry, that is to be 65.3. So this one's right here. Okay, so I would just be writing them here. Okay, so these are to be the parameters that we will be needing for this trial section. So I would just be moving them here. So from that, guys, you're already done here, you're already done here, and we have already selected a member, which is W10 by 60. So the next thing that we would be doing here is to check if the section is really adequate by analysis.